This is Carter Colligan. I'm explaining my Project 2 problems turn in. My first problem, I have coffee inside of a cup and then my hand on the outside of the cup. I'm going to determine the temperature profile of that cup. This problem covers conduction, convection, boundary conditions, deriving, solving, and cylindrical coordinates. To do this, we must assume the thermal conductivity is constant, the heat transfer is one-dimensional, and no energy is created, and finally that the heat transfer is steady state. We want to find the temperature profile of the cup and by first deriving the 1D cylindrical equation and then applying boundary conditions. First, to define the 1D cylindrical equation, we take an energy balance and we can simplify that by the fact that the process is steady state and there's no energy generation. And then from there, we can divide by area times delta R. And then we can take the limit as delta R goes to 0. And from there, we're going to end up with this final formula. Once we have that, we can simply go from there and integrate once and apply a boundary condition that the convective force at the inside of the cup equals from the coffee equals the heat flux. And then from there, we can solve for C1. And then next, we're going to integrate one more time and apply another boundary condition that the temperature at the outer equals the temperature of the hand. And then from there, we can simply simplify the equation down for the temperature profile. In the end, we end up with a temperature profile that's based off of the radius you want to determine the temperature at, and you need to measure the temperature at the inner of the cup. My next problem is a lumped sum problem. It only covers the learning outcome of a lump sum. And to do this problem, you have a 1,000-degree hot stainless steel ball that's cooled to 25 degrees, and we wanted to determine how long that takes. To do this, we must assume the thermal properties are constant, heat transfer is constant over the whole sphere, and that the Biot number is less than 0.1 for lumped analysis to apply. And then to start this problem off, you just take the lumped analysis formula, e to the negative bt equals temperature minus temperature infinity divided by initial temperature minus temperature infinity, and then solve for time. First, you must solve for the b, which is like the time coefficient, and from there you can determine the time is 18.6 minutes. And to verify the results of the lumped analysis, we take the Biot number, which is equal to 0.0151, which is less than 0.1, and therefore lumped analysis applies. For our final problem, we have a CPU that's giving off heat, and we want to determine the temperature of the CPU given the resistances is everything. This problem covers conduction, convection, resistance, and uses Cartesian coordinates. To do this problem, we need to assume that steady state, the heat transfer is one-dimensional to the fins are adiabatic tip, and that the heat transfer from the tips is negligible, and all heat transfer coefficients is constant. To do this problem, we first find the efficiency of the tip based off the hyperbolic tangent times ml divided by ml, and then from there we determine that m is equal to 4.63 meters to the negative 1, and then we need to find the corrected length, and the corrected length is equal to the length of the tip plus the thickness of the tip divided by 2, or 0.02 or 5 meters for this problem. And then from there, we simply calculate the efficiency of the tip, and then from there we can determine the heat transfer by the tip equals the efficiency of the tip times the convective force, which is the h times the area of the fin times temperature at the base of the fin minus T infinity. From there, we can determine the heat transferred by the unfinned surface, which is the area unfinned of the heat sink, times the H of the aluminum of the heat sink, and then we take the temperature at the base minus T infinity. From there, we can set up this Q total formula right here, and that Q total formula, we're going to solve for temperature base, determine the base of the heat sink temperature, which is 37.8 degrees. From there, we can determine the temperature of the CPU based off the resistance of the aluminum, the thermal paste, and the silicon. We take the resistance of all those, which is equal to the length of that material divided by the thermal conductivity of that material, and then the area of that material. We add up all those resistances to get the REQ, which is 0.0773 degrees Celsius per watt. And then from there, we take the formula, which is heat transferred, equals the temperature of the CPU minus the temperature of the base of the heatsink divided by the REQ. And then from there, all we have to do is solve for temperature at the CPU, which in this case is the heat transferred times the REQ plus temperature at the base. And we determine the temperature at the CPU is going to be 41.6 degrees Celsius. Thank you.